All right. Good morning, everyone. Are you ready for another week?
Oh, yeah.
There we go. Somebody's awake. All right. Well, then let's quickly review. So one thing that I owe you is to post example test. Our test is the Wednesday in 10 days. Everybody has that on the calendar working towards it? All right. So basically, I will post the examples, and then you can ask questions and work through it. But also, just so that you see the format. In general, the way we have this exam, typically you should be able to finish it in an hour and a half or so. And there will be questions, programming questions, but you will have to write down the code by hand. Okay? So there will be no computer allowed during the exam. And you will be able to have a cheat sheet, so front and back with any formulas that you like. The only thing that I don't want to see on the cheat sheet is solved problems. So definitions, name of the functions and how they work, but not like a piece of code that does something. Okay. So essentially, I expect you to know that much yourself, and you just have a cheat sheet to remind you of definitions that you might forget. And basically how functions are used, all of those things, those are all allowed. That little table of all of the plot possibilities, coloring, and I don't know what else you can do with the markers. So that's a perfect thing to go on a cheat sheet so you can look it up if you need to. Okay? But again, no solved problems. So let's finish. Today we will finish up our lecture on unavoidable errors in computing. So we have started with avoidable errors in computing, and that's basically typos and bad organization of the code that can basically over time introduce errors. So that's something that you just have to look for and constantly work to improve, but it can be avoided. We often call those bugs. Now that there is unavoidable part is that it's simply that we have finite space to store things. So how does that? Last time we actually had, so we had the representation of integers and real numbers on a machine that can introduce errors. And then we also have computation with the numbers. And for instance, that's called finite precision arithmetic. So just a quick review of the last thing we did last time. So we could have either integers, computation with integers, or floating point. Floating point is basically a name for a real number in computers. Okay? And just like in scientific notation, when I go times 10 or divide by 10, my point moves, right? So that's where the name is coming from, floating point. So basically, if I have integers, 2 plus 2 is 4, that's great. But if I try to divide 51 by 17, that's still an integer. That's great. But if I try to divide 4 and 3, and I store it as an integer, there will be a roundoff there, and there will part of that number will be chopped off, and it's going to be stored as 1. So often if I define my, so in MATLAB we don't go and define a variable what it should be, integer or real number, because in MATLAB, like, the moment you assign a variable, it's going to be a double precision real number. But if you actually forcefully said, like, this should be an integer, and you can do that, okay, then if you divide 4 by 3 and try to store it as an integer, it's going to be stored as 1. Okay. So that definitely, there is some rounding down that always happens when you try storing it that way. Now in floating point, okay, we know that 4 divided by 3 is 1.333333333333333 and so forth. And we also know that computer cannot go forever. Okay? So somewhere here there will be a chopped off part that cannot be stored because it cannot have infinite number of 3's. And then if I try to multiply it, let's say that all I can store is this. Okay? If I try to multiply it back by 3, I'm going to get 3.999999999. For all intents and purposes, it's a 4, but there is a little bit of error in here. Right? So again, the computer will actually store more, but just for this example, let's say that it stored only these. Okay? When I would multiply it by 3, I would not get my 4 back, okay? But something close to it. So basically, I will also have some round-off errors when I have numbers. This is the example where I have numbers that are really apart in terms of orders of magnitude. So let's say that I have 10 to the 10 and 10 to the minus 10. Okay. Basically, I don't have enough significant digits to store both of these. If you remember, we actually have to, just a second. So we have to, let me just go quickly to, we have that the way I'm representing the real number is I'm gonna do a scientific notation version of it in binary decimal, in binary system. And then I will gonna be 1 plus p times 2 to the t, okay? So if I have two numbers where these exponents are very too far apart, it's very hard to find one exponent that works for all. Okay? So basically then this p would have to have a really large number of significant digits to actually fit both 10 to the 10 and 10 to the minus 10, which are 20 significant digits apart. Okay? So if I don't have that much space to store it correctly, then the 10 to the minus 10 will simply get cut off. Okay. So basically, if I have numbers that are very far apart, I'm going to have rounding off. Also, I might actually have something like I do this, and then I do subtraction, okay? Because this was rounded up, I'm going to get a 0 at the end. Even though if I just rearrange things a little bit, if I actually did this in different order, I would get 10 to the minus 10, which is the exact number. Okay? So these are little things that can happen. These days, computers are getting smarter and smarter, so they will actually go and examine this and rearrange in order not to get this error. Okay? But if it's done in this order, there will be an error. Quadratic formula is a very good example of when roundoff error can occur, and that's actually, there's a problem on your homework that is related to quadratic formula. Basically, you have that solution to the quadratic equation, ax squared plus bx plus c is equal to 0, is minus b plus minus square root of something divided by 2a. And this is essentially this plus minus square root of something is where you could have two numbers that are very, like minus b and that square root of something could be very much far apart. Okay, so that's where I could actually have this adding or subtracting a really small number to a big number. Okay. Or if or you could actually have a situation that they're nearly identical. Okay. And quadratic formula is something that's solved a lot, so that's going to show up as a problem in numerical methods. All right, so let's quickly review everything that we had in this lecture. We're used to a decimal base 10 system representation of numbers in terms of powers of 10. Okay, so 158 is 1 times 100 plus 5 times 10 plus 8, and that's something that is kind of embedded in our understanding of how to do numbers. And why did we say, why is this decimal system so common? We have 10 fingers, so that's something that we could work with. So base 8 doesn't make as much sense, but mathematically there's nothing wrong with base 8. Okay, base 7, base 16, you name it. Now in practice, we're using mostly base 2. Okay, so how would you represent? Can you do a quick exercise now on a piece of paper? Please represent 158 both in base 8 and base 2. And just to make it easier, I did put the powers of 2 and powers of 8 up there. You can definitely expect some of these conversions similar to what you have on homework on the test. Get for my base 2. So let's do base 8. I have powers of 8, 1 to 8, 64, and the next one, 8 times 64, is way above this number, so no need to look at it. So let me take this biggest power of 2, 64. How many times can I fit 64 into 158? Twice. Because if I go 3 times, I'm going to go to 200 and something. So 2 times 64 is 128, right? So then there is 30 left. So I have 2 times 64, and then 30. What is the biggest power of 8 I can fit into 30? 8, how many times? 3 times 8, and that's 24. And then there's 6 left. 6 is just 6 times 1. So this is 8 squared, 8 to 1, 8 to 0. So what are my digits? 2, 3, 6. Yes? How about base 2?
Do we need to include the zeros? Oh no, it's just 2.
If I had, I mean, technically, yes. So if I asked you, well, this is not represented, but this is same as however many zeros you want at the beginning.
On the test, we have to include the zeros?
But
No.
base 8 is not what we use for computers. So, no. We fill in with zeros when I want to fill things into 1 byte or 2 bytes or into computer memory, and in that case, we are actually using base 2. But I mean, it's not wrong if you add zeros at the beginning. And base 2, so what is the largest power of 2 that I can have there? 128, and that's 2 to the 6. Is it 4, 7? And then I have 30 left. What is the largest power of 2 I can fit into 30? 16. And 16 is 2 to the 4. And then I have 30 minus 16 is 15. The largest power I can put into 15 is 8. And then I have 7 left. The largest one is 4. Then I have 3 left. Yes? So I'm going to put, let's now do this just like it is on a computer. So I have, in 1 byte, I have 8 bits. And this is going to be 1, 1, 1, 1, 1, 0. Did I? No, 1, 0. Because this is my power. 0, 1, 2, 3, 4, 5, 6, 7. And then if I was writing this down, I would put 2 so it's 3. Yes.
Will the last one be 0?
I had a 3. Okay. 3 plus 4 is 7 plus 8. 15 plus 16. Oh wait, no, yes. It wasn't 15, it was 14. So yes. Because 30 is 16 plus 15. On a Monday morning without coffee yet. All right. So that is basically representation of numbers. Now, if I had 2 bytes on a computer, what would I do? If I was fitting this into a 2-byte number, I reserved, so when I'm fitting it, I reserve 2 bytes. So, in fact, I have to fit it in there. There would be zeros, there would be 8 zeros. Now, signed or unsigned integers, what is the difference?
Extra 1.
Right. So, I have to know whether my number is signed or unsigned, because in the case of a signed number, I take that first bit and it's interpreted as plus or minus. It's not part of the number. So this number, if it were interpreted as a negative number, okay, what would that number be? If I had a signed 8-bit integer, this leading one would be interpreted as a minus, okay? And then it's going to be negative whatever is left, okay? So it would be a negative, what is 158 minus 120? Negative 30, right? Yes?
So the first bit is, if the 1 is negative, it's 0.
Yeah.
So how do we write the same number and make a negative on 8 bits? Or can you not do that?
If you have only, you always have 8 bits, so in that case, and then your range is changing, right? So it's very important to know what it is that you stored in memory, right?
How do you
And how do, huh?
how do you call it to let the reader know that it's starting with a negative?
If it's just an array stored on your computer, you don't. And that's what the problem is. Okay? If you otherwise, any data that comes with a known format, like .docx or .tiff or .jpeg and so forth, there is a header at the beginning of the file that has a specific format that lets you know what the type of the numbers are inside it. So for instance, if you're storing an image, images are just arrays of numbers, okay? And those numbers, those numbers are interpreted as colors, okay? And you can choose what colors to represent them. So that's you can do different color maps and whatnot. Now those numbers, so JPEG or TIFF or some of the common image formats, they have a header at the beginning that says, oh, in this thing you have unsigned integers of 2-byte integers or signed 2-byte integers and so forth. Okay. So there's something at the beginning that computer reads, and then they know how to read the rest of the number.
So on the exam, if you were to give us this number and say like make it into a negative integer, we would say like not valid because.
Right. So yeah. So it could be. You cannot have minus 158 as a signed 8-bit integer. Yes.
What if you not have 2 bytes?
If you have 2 bytes, then the leading 0, then there would be a bunch of zeros at the beginning. And in this particular case, if that 0 is part of the number or not, it doesn't matter. It's not. It's a positive number, 158.
So this means you have a negative and 0.
So I have to have, to interpret a negative number, I have to have a leading one. Okay. Right. Oh, so this is the solution. Right. Now, how does the process work for representing, for instance, 0.0054? Let's say that I was actually working in base 10. How would I proceed? And I was storing in base 10 in some imaginary computer. What's the first step to do? Scientific notation. So this would be 5.4 times 10 to the minus 3. Okay. And then I would be separately storing the sign, 5.4, and then exponent. An exponent can also have a sign. Okay. And we reserve within however many bytes we have, we reserve certain number of bits for each of those. Okay. Now, what I would actually do, I would represent 0.0054 in base 2, okay? And basically then once you have a base 2 in scientific notation, it would be, for instance, 1 point something 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 times 2 to the exponent, okay? And in that case, we convert it in this format 1 plus b times 2 to the t, okay? And I always, in scientific notation in binary world, I will always have 1 point something times 2 to the exponent. And therefore that 1 I don't need to store. So I typically remove the 1 and don't store the 1. I just store what's left after deducting 1. And I have, in case of single precision, I have 23 bits reserved for this mantissa p. And 8 bits for exponent t, okay? And 53 bits for mantissa if I have double precision, and 11 for exponent t. And one of those digits, 1 out of 23 and 1 out of 53, 1 out of 8 and 1 out of 11 is reserved for a sign. Yes, questions? So I just want you to know like how it's roughly done and where the errors could be. And that's why I have those ranges that we mentioned. Okay. So essentially, my double precision numbers can go from minus 1.8 to 10 to the 308. Up to minus 2.23 times 10 to the minus 308. So this is this usable range. If I'm in absolute value larger than this number, then I'm going to go into overflow. And same thing happens on the positive end. So if my absolute value is very large and I, for instance, cannot figure out this exponent is much larger than 308, then I'm in overflow. And I also have close to the 0. I can represent 0, no problem. But if I have a number that is in absolute value less than 10 to the minus 308, then I have issues. And we call that underflow. And then also we know that like in between the numbers, here we have sort of gaps because I'm chopping off certain number of digits. So for instance, let's say that this number was actually, and I'm going to exemplify things in decimal world again. If this was actually 5.43210 and so forth, and I could only store 3 significant digits because I don't have enough space, the rest would be chopped off. So there's certain gaps in the numbers that I cannot fit in. Okay? They're kind of rounded up or down. Okay. So can I properly represent 0.1 times 10 to the 708? No. That is my overflow. Okay. Can I do this? No. So that is called, this was overflow, this is underflow because it's in absolute value too small. And it's simply I don't have enough space to fit in this type of exponent.
I thought both sides were overflowing in the middle.
Underflow. Yes, and this is the middle.
Oh.
Okay, it's close to the 0. So you got it right. Okay. So essentially, there is no space to represent number 708 because I have only 8 bits for exponent t. Okay? 8 bits. That's minus 127 to 127, 2 to the minus 127 to 127, if I have a single precision. And if I have double precision, okay, it would be minus 2 to the 10 roughly to 2 to the 10. And when I convert that to 10 to something, this is way above the number that I can do. Okay? Is everybody clear on that? So if I have only 8 bits for exponent t, well, my exponent t can be between minus 127 and 120, minus 128 and 127, right?
For every bit has to look at its own range. Like for every bit has to look at its own range. The 8 bits, the 23 bits, they all have a distinct.
Right. And we went over that. So, for instance, here, the largest number I can represent with 8 bits is if all of these are ones, right? And that gives me the limit, essentially, if I have integers. And exponents are integers. All right. So if you need MATLAB to figure out what is the maximum and minimum of all of the ranges, you can use int max, int min, real max, real min, and you also give it whether it's int 8, int 16, and if you want unsigned, then it would be u int 16, u int 8, and so forth. And real max, you give it single or double to get the ranges for different precision. Okay. So I'm going to just define this. So if I have 2 numbers that are very close, they cannot be distinguished any further if their difference is very small. So this is this part where basically no matter what, after a certain number, no matter what I have behind, I'll have to chop it off, essentially. So in order to help that, you typically use double precision, and MATLAB already does. So, but if you're in any other programming environment, you will have to define whether you have single precision or double precision numbers. So technically, the way you test this, what this number is you keep making this number small. So let's say you start from 1. And if it's just 1, 1 and 1 is 2. Okay, and that's fine, that's larger than 1. And you keep reducing this number, making it smaller and smaller, for instance, dividing it by 2. Okay? And as you keep dividing by 2, at some point, 1 plus this very small number will be simply equal to 1. And you can test that. Okay? So you can actually test what this precision, machine precision is. And in your homework, you have a little algorithm that does that. Okay? That you have to implement and find what this number is. Okay? So again, at some point, this becomes too small and it simply gets chopped off when I'm trying to add these two. Now, that little algorithm is just approximately this precise limit of this epsilon, but it's good enough for practical purposes. All right. So this is going to be essentially, there's an algorithm in your homework to do that. All right. So again, errors in computing are unavoidable. We use finite number of bits to represent a real number or an integer, either way, and that introduces errors. I could have simply limits of how large or how small numbers can be. And I can also have round-off errors where basically I have to discard certain number of significant digits in a number. Finally, there is a truncation error. What is a truncation error? That's the thing that we did at the very beginning of this class. Something to do with mathematical formulas. So if I have like a sum that goes to infinity, well, you can't go to infinity. You have to stop at some point. So the fact that you're stopping means that you're truncating a part of it. Okay. And the best example for that is Taylor's formula. Taylor's formula is also, if you remember anything from your calculus class, Taylor's formula is it. Especially for numerical methods, it is used a lot. So one thing that we will not do in this class, because this is an introductory class, is later when we introduce numerical methods, basically analyze how precise they are and give some sort of limits on the error that they make. And Taylor formula is used left and right for that. It's the biggest practice of Taylor's formula ever, is to actually prove that your numerical method has error within certain range, and you use basically Taylor's formula for that. All right. So this is this example of Taylor's formula. This is the example that we did in class. So f of x is some we're working in a neighborhood of x0, so it's the value of f at that neighborhood, and then I need first order derivative, second order derivative, and so forth. And somewhere here I stop. So depending how many of these terms I use, I get better accuracy, but I will still have an error. Okay. So if I'm computing number this way, then I will have this approximation and some sort of error, and we can figure out what error is. Now, what is relative, what is absolute error? The other way around. So absolute is just the difference, and relative is I kind of scale it with the number itself. And that is important if you're comparing different things. Okay? So as long as you're just comparing a set of numbers with itself, that's fine. But if you want to see how you did on Monday versus Tuesday versus Wednesday, right? There's possibly going to be slightly different ranges, and you want to see relative error rather than. So typically, if as a default, go with relative error. Just later on when you do this in different classes. We did these first two examples in class, but this one we didn't. So let's do this to wrap up. What is the representation of 0.75 in base 10? In base 2. So key will be again to express this in terms of powers of 2, but those powers are actually negative. This was likely the most confusing part of the lecture. Switch to base and everybody is good. Before you answer this, if you're confused, 0.1 in base 2 means what? It's 1 times 2 to what? Negative 1. So if I had numbers 101.1 in base 10, I understand, and I don't even think about it, that this is 1 times 10 to the 2 plus 0 times 10 to the 1 plus 1 times 10 to the 0, and then plus 1 times 10 to the minus 1. Now do the same in base 2. It's 1 times 2 to the 2 plus 0 times 2 to the 1 plus 1 times 2 to the 0 plus 1 times 2 to the minus 1. So this is 0 times 2 to the minus 2 to the 0 plus 1 times 2 to the minus 1. This is actually 1/2. Now, in the same spirit of what we had before, if I looked at the powers of 2, that are negative powers of 2, I have 1/2, I have 1/4, and so forth, right? 1/8. So what is the largest one of these that I can fit in here? And then I have 0.25 left. So what is the largest? So this is 1 times 2 to the minus 1 plus 1 times 2 to the minus 2. What is that in the binary? Kind of makes sense. Just don't think about it, right? Just put the dots and keep going. We know negative numbers. So any number I could do this way. So I can, again, do any number. All right. It is finally time to actually start working on numerical methods. So far, everything we did was essentially preparation for it and some essentials. And now we will actually put it together. I will share the lecture slides right after the class. Actually, I can. Do you want them immediately, or are you okay going without? I could upload them right now. Right now? Okay. There's somebody who wants to have slides to look at. We will do that. What else? Lectures. Oh! I haven't uploaded any of these? And nobody said anything? Wow. I actually have a recollection of uploading, but I guess not. Okay, open, then upload. We will fix it now. Upload. All right. So now you have all of the lectures. So we will start with lecture 5. Go to the garden and find some roots. No. We're gonna start with some root finding. I introduced the root finding as one of the problems at the very beginning in our introduction. And here's a slightly, there I used Peng-Robinson equation, which we will come back to. But here's another example. So let's say that I have a martini glass filled to 6 centimeters of depth. And I know that it contains roughly 216 times pi over 3. And that's milliliters. Why is it micro? Why is this milliliters in Greek letters? I don't know. My computer decided to convert something. Micro. So mu is m and lambda is L in Greek letters. So ml somehow we converted to that. Anyway, maybe just to see whether we're paying attention. Now, how deep must you fill wine glass to ensure that it contains the same amount of wine, but I have a different shape? So my martini glass has a conical shape, and my red wine is sort of, we're going to assume, that's kind of a little bit of a bad assumption, but that it's actually part of a sphere. Okay. So with that assumption, it's a funky red wine glass. Okay. It's Austin kind. A little bigger. So let's go with the volume of the spherical cap. I know for a spherical cap, if I have a spherical cap geometry and it has certain height, and I have radius r, and then I have this shorter length a, then my volume of this cap is pi over 6 times h times 3a squared plus h squared. Now I know Pythagoras rule. So here, actually from this triangle, I know that a squared plus h plus radius minus h, which is this length squared, is equal to r squared, right? So that gives me a function. What is a in terms of r and h? And if I substitute that in, then I get what my volume of this cap is in terms of h and r. Now, this is essentially for a given sort of radius r. This is a function of h. Okay. So what it really comes down to is finding, hey, what is the h that gives me precisely this volume? And the way we will formulate all of these problems is that instead of saying, oh, volume equals to number, this number might change as I have different problems. We're going to formulate them all so that I have a function, in this case of h, that is function of h is equal to 0. So whatever problem that I'm working on, I have to reformulate it and fit it into something so that I'm looking for h, okay, such that f of h is equal to 0, or looking for x, such that f of x is equal to 0. And this form of f comes from my problem. So in this case, I want volume to be a certain number. So the simplest thing is to put that number on the right-hand side, and then I have this formula for volume minus the number that I need is equal to 0. And that's my formula function. And why? We want to have always the same. 0 is always 0, right? So as long as you put it in that form, then all of the methods that we develop for one of these cases can be applied in any other case. So we want to have sort of like a formula that we can fit many problems to. And once I develop solution for one type of the problem, I can actually go and use it. Does that make sense? Okay. So one of the trouble here will be actually whatever problem I give you on the paper, formulating it so that you get this f of something is equal to 0, and then you're looking for that something. And h that satisfies this equation, in this particular case, we call root of this equation. Okay? Now, if this equation was actually a quadratic equation, I would need no course on numerical methods to find it. I have a formula for it. But often I will have a nonlinear cubic. There are some formula for cubic, but they're equation, but they're not very popular. I might have sine of h here or something of that sort. It might get actually quite complicated here. And then I know I don't have a formula, so I need a numerical method, so I need an approximate way to find the solution. Oops. So another example, and this is the example that we had at the very beginning of the class, is Payne-Robinson equation of state. You will learn about it in thermodynamics. Okay? But it basically describes real gases, not ideal gases, but real gases. So what is the problem? If I have ideal gas, I have a very simple formula that relates my pressure, volume, and temperature. So PV is equal to RT. R is a constant here. Now, gases that we deal in petroleum engineering and otherwise, most of them are not ideal. Sometimes ideal is a good approximation, but for gases in a reservoir that are heavy organic molecules and can have very high pressure and temperature, the ideal gas law is not it. So in those cases, we have this rather complex relationship. Okay? And next time, we will actually figure out how to convert it in this. If I'm, for instance, looking for the volume that satisfies this, I have to convert this into f of volume is equal to 0. So that's the algebra part of the problem. All right. I see you on Wednesday.
You said you'll be uploading the practice.
Yes.